Hello, I'm Adam Baker. I'm a rocket engineer and a visiting fellow at Cranfield University. I'm going to cover the basics of rockets in this short video. I'm going to elaborate why both altitude and velocity are needed to get payloads into orbit around the Earth, and how we can use the rocket equation to define exactly what extremes of velocity a rocket needs to deliver satellites into orbit. I'll also explain a little more about rocket engines and the rocket propellant or fuel tanks that they carry and how they need to be designed in order to do that job efficiently. And I'll finish up by covering some of the key other things that a rocket has to do in order to put its satellites into space safely and efficiently. And I'll remind you what the key parts of a rocket are.
Large and small rockets all burn propellant in order to gain altitude and velocity in order to reach space. Through Newton's third law, or action equals reaction, expelling propellant or rocket fuel in one direction makes the rocket accelerate in the other direction. Rocket propellant might be solid, or for example liquid, oxygen and kerosene. Burning and ejecting this at high velocity causes the rocket to travel in the opposite direction, higher and faster, until it is flying above the atmosphere and heading towards space. The rocket has to launch and fly above the atmosphere at just the right velocity to reach orbit. Too slow and it hits the ground or ocean before reaching space. Too fast and it escapes from the Earth into interplanetary space. Travelling at 8 kilometres or 8,000 metres per second is just about right for Earth orbit. The rocket must also turn to travel horizontally, or it will decelerate when it runs out of fuel and fall back to Earth. Going straight up is not enough. How fast and how far? Well, 8 kilometres a second is much faster than a rifle bullet. In fact, orbital velocity is so fast that you could go from one end of the UK to the other, about 874 miles by road, or over 1,200 kilometres, in around 2.5 minutes. But in terms of distance, space is only about as far away as London to the Isle of Wight. That's about 100 kilometres. So getting to space is easy, it's not far away, but staying there is hard. So, how can a rocket actually achieve this extreme velocity of 8 kilometres a second to reach orbit? To understand how it does that, we need to look carefully at the rocket equation. How does the rocket engineer achieve that magic delta V, or the velocity change needed to go from the Earth's surface to orbit? Well, they need two things. And the first is exhaust velocity. That's a measure of how efficient your rocket engine is. Think of it a bit like miles per gallon. We'll come back to that in a later class. The second is the mass ratio, or the initial mass of the rocket compared to the final mass, the difference being the propellant that it's burned. And this is also a measure of how efficiently your rocket carries all its propellant or fuel. These are linked by an equation, the rocket equation, and here's how it works. Here's the rocket equation. This shows delta V is made up of two parts. The first, ISP, is directly related to the delta V. So, the greater the ISP, or the more efficient you can make your rocket engine, the greater the delta V you can achieve. But you can't infinitely increase ISP. There are limits on rocket engine performance, as we'll see in a later class. Looking at the rocket equation again. So the other thing you can change as a designer in order to affect delta V is something called the mass ratio. This is the ratio between the initial mass of the rocket and the final mass of the rocket, or it's related to the amount of propellant burned, but it's hidden inside a logarithm. So to change delta V a little, the mass ratio has to change a lot, and making a high mass ratio rocket, or a light, structurally efficient one, is really difficult. Okay, so that was pretty hard. Getting into orbit is hard, and the rocket designer can't change much to make things easier. Fortunately, getting into orbit from the Earth is actually the most difficult manoeuvre you might need to do in space. There are other things you might want to do that are easier. Well, spacecraft often change orbits, that shape and size. This manoeuvre is perhaps 10 to 20% of what's needed to get into orbit. 1 to 2 kilometres a second. Easier, but still fairly hard. You might want to dock with another spacecraft. That's much easier, assuming spacecraft are moving in similar orbits, so it's only a few meters per second to deliver. But really important is to be able to deorbit at end of life to avoid creating more space junk. That's not too difficult, perhaps about 1 to 5% of the delta V to get into orbit in the first place. Let's put some numbers in and find out just how hard it is to put, say, a 1,000 kilogram or 1 ton satellite into orbit, orbital velocity. So putting those numbers into the rocket equation, there's the equation, there are the numbers. We need to reach 8,000 meters per second, which is orbital velocity. And in the rocket equation on the right, the ISP or efficiency of our rocket engine is, say, 3,500 meters per second, which is a typical value. We're trying to work out what R, or the natural logarithm of R, actually is. Well, rearranging, it's easy to work out that log R is about 2.5, or if we want R, that's over 12 times. Remember, R is the start mass of the rocket divided by the final mass after all the propellant's burnt. So the rocket full of propellant is 12 times heavier than the empty rocket. Wow! Recall that R is rocket and satellite and propellant divided by empty rocket and satellite, which is just 1,000 kilograms. Doing this a bit more maths gives us propellant, 11,000 kilograms, or 11 times the mass. So, this shows us that the rocket required to put the satellite into orbit needs to be over 90% propellant. That's a huge flying petrol tank, and it's all got to be light enough so that you don't waste propellant taking too much rocket itself, tanks, engines, into orbit, or there'll be no room for your satellite. So let's put that number in some perspective. A Ford Focus, a small family car, weighs about 1.5 tons and takes about 45 kilograms of petrol. So that's about 3% of its mass as fuel. Not much really. In contrast, a passenger aircraft such as an Airbus, the big A380, might carry almost 47% of its 450 tons of gross weight as fuel for a journey across the world. That's a bit more. But completely overpowering all of this, a rocket launch vehicle going into space needs to carry more than 50% of its overall mass as propellant. That's huge in comparison to other forms of transport. And it's only used once, then it's thrown away. But that's not all. As well as delivering that performance to push through the atmosphere and accelerate to reach orbital velocity, the rocket must not break the satellite during the ride. It must be super accurate in delivering its payload to a very precise orbit. It can't break down anywhere on the long road to space because there's no AA or RAC up there. And finally, it must be affordable, so not a private jet, but a bus. Doing all these things together is challenging for even the best engineers. So to finish, a rocket's made up of 3 parts, starting with the payload or satellite. This first tiny part is less than usually 1% of the whole rocket mass, and that gets accelerated to orbit or gets the delta V we're trying to deliver. The rocket engine, or engines, go at the other end of the vehicle. They're also small, but the hottest and working under the most extreme conditions and the most challenging from an engineering perspective. The biggest part of the vehicle is a giant flying propellant tank. You can think of it as like a huge fizzy drinks bottle, but designed especially for rocket propulsion. Add a wrapping and a nose cone and some avionics, and voila, you have the basics of a rocket launch vehicle and one of the key tools to design it, called the rocket equation.